seminar in this semester. So before I start this seminar, I have a question. Does anyone know where is the institute credit card? It is not in the office. I need it for the lunch, but
it's okay.
Okay. Thanks. Okay, but thanks. Okay, so today's speaker is Meynet from the University of Geneve. Okay, so let me introduce his career first. He took his PhD in the University of Geneve, and he had a postdoc position in Belgium. And after that, he came back to the University of Geneva, and since 2006, he's a full professor. And he's working on the evolution of stars and the stellar structure, evolution, and the chemical evolution of the stars. I think this topic is very important, not only in the started science, it's related to the galaxy formation, galaxy physics, and cosmology. So I'm so excited to invite, we can invite him to this seminar. Okay, so let's start.
Thank you, and good morning, everybody, and thanks to Professor Ravi Telet and also Dr. Sho Shibata for having organized this seminar, inviting me here today. So I will address some different topics, maybe somewhat unrelated, but the common features among all these topics is stellar physics, as you will see in a while. Before to go directly to the topic, I would like to maybe just to see how we can change the diet. Yes, okay. I would like to pay credit to the person with whom I am collaborating in Geneva. This is the team in December 23. And this is a rapid outline of my talk today. I wanted to speak about the physics of rotation, but it was too long. So if you want to know more about the physics of rotation, maybe somebody can ask me a question at the end. So let us begin directly with the challenges. Actually, stellar physics is a very old topic, and many people think that we know everything about the stars. And indeed, stars in many ways are very simple objects, because most of the lifetime, more than 99% of the lifetime, even more, they are at hydrostatic equilibrium. And from very simple principle of physics, we can deduce important quantities about the star, like the central temperature, central density, and so on. On the other hand, stars are very complex objects too, because they host a whole series of hydrodynamical phenomena, sometimes magneto-hydrodynamical phenomena. And these, as you know, are very complex to simulate and to model. I have just put here a few of these still present challenges when you want to model the evolution of stars. There is first the convection. As you know, convection, the convective cores, measure or gives the quantity of fuel that is available to a star. So it determines its lifetime, for instance. It determines its chemical output. Then there is the mass of it. Stars, especially the massive ones, are losing mass, sometimes at high rate. Do they lose mass by very rare and very strong outbursts, or do they lose mass more regularly? Rotation. Rotation is a very important mechanism because it's a bit like, you know, when you take a spoon to mix the sugar at the bottom of the cup of tea. Actually, during the main sequence, typically in massive stars, you have that in the core of the massive stars, you have a lot of nitrogen produced by CNO cycle reaction. And this nitrogen is in the core of the star. But if the star is rotating, you can induce many turbulence or many instabilities, either hydrodynamic or magnetic ones, that can bring some of the nitrogen to the surface and change the surface composition of the star, but also change deeply its evolution. Then you have the magnetic fields, which are tightly related to rotation because magnetic field can force the stars, if the magnetic field is strong enough, to rotate as a solid body instead of having differential rotation as a function of the radius. And you have the multiplicity. Many stars are in binary or even in triple or quadruple systems. And of course, here you have to account for the gravitational interaction between the stars that are near enough. What is worse is that all these processes have to be accounted in a good way at the same time. They are interacting. You cannot just study one isolated from the others. So I will not take so much time to describe the physics of all these, because every of these topics could be the topic of one seminar, I would say. I have chosen rather to illustrate some of the importance of them in some astrophysical questions. And the first of them is the star-planet interactions. I am a little bit shy here to speak about planets because you have very strong groups about planet formation. And I am not at all on this topic, I must say. But a few years ago, we were interested by modeling in very simple system, one star, one planet, not interaction with the other planets, and how the orbit of the planet is modified just by tides. And as you will see, in order to do it right, you have to describe accurately the evolution of the star too. You know, it's not just a point mass. As you know, the interaction between a star and a planet can occur through gravity. It's tidal interactions, but the stars during the red giants can lose mass by stellar winds. So winds can also interact with the planet. It can interact with the radiation. Radiation can evaporate some atmosphere of the planet. And you can have also interaction mediated through magnetic fields. I will focus on tidal interactions. Tides come from the fact that when you have a source of gravity, the source of gravity will perturb the gravity field by different parts of the stars differently. So it will produce two things. It can deform the stars, giving it a new equilibrium shape. These are called the equilibrium tides. But also, because of course the source of gravity, which is the planet, is moving, it can drive waves inside the stars. And these are called the dynamical tides. You have, of course, the tides induced by the planet on the star, and this is what I will speak about now. But you can have also the tides induced by the star on the planet, which will act on the rotation of the planet. But I will not deal on this topic here. I have an example here of what of an effect due to equilibrium tides. You know, if you had the planet which is rotating at the same speed as the star, we will have the star which is deformed by the gravitational attraction due to the planet, and both will rotate simultaneously with a bump aligned with the planet. But you know, the stars can have a speed or a velocity on its orbit larger than the rotation rate of the star, in which case the planet will precede the bump. Here we are on the contrary, in another case where the planet is moving slower than the spin of the star, and the planet is behind the bump. So this bump will attract a little bit the planet. It will speed up. It will give angular momentum to the planet at the expense of the angular momentum of the star. So the star will slow down. The orbit will become larger because the angular momentum is increased. And so you have a change of the orbit and a change of the spin of the planet too. If we look at and these are the typically equilibrium tides, and if we look at the expression showing the way the radius, here is a circular orbit that we have assumed, the way how the radius of the circular orbit changed this time as a result of this interaction. And we assume that we look at the effect of the dissipation of time in a convective envelope, because stars can have convective envelope or radiative one. If we look at convective envelope, we have this famous formalism that has been obtained a long time ago by Jean-Paul Tsai. A is the radius of this circular orbit, and this is as a function of time. And if you look at the expression on the right, many points involve characteristics of the stars that are changing with time. Typically, the mass of the convective envelope. Sometimes the star has no convective envelope. The term is zero. When the star becomes a red giant, convective envelope appears very deep, which extends when the star climbs the red giant branch. It becomes more and more prominent. You have stellar radius, and you can see it's at the 8th power. When the star becomes a red giant, the radius can increase by a factor of 100. 100 to the 8th, it's a big number. So the tide will be very large during the red giant branch, typically. And you have the spin of the star, for instance. So what I mean here, in order to really make this computation more accurately, you have to simultaneously compute the evolution of the stars together with the orbit of the planet. You have also other terms that can change the orbit of the planet. First of all, the stars can lose mass, which is the case during red giant branch. This change also, this gives some term here. The planet can lose mass also if it is evaporated by the radiation of the star. You have then other terms which come from the fact that the planet is not moving in an empty space. It moves into interstellar medium, interplanetary medium, let us say, more than interstellar. And so it feels some friction. Some matter around can be redistributed by the gravity of the planet itself, producing some accumulation at some place, producing a drag force. And you have the tides, the last term. So a few years ago, with Giovanni Privitera and PhD student in Geneva, we opened new lines of research in our group of stellar evolution, which are the computation of orbit, but following exactly, or let us say not exactly, we have to be humble. With, let us say, complete stellar models, the evolution of the star. And so here we accounted for one Jupiter mass planet, around 1.5 solar mass stars. And these stars begin with an initial rotation, which is 10% of the critical velocity. The critical velocity being the velocity, the rotation period, the rotation velocity of the stars, at which the centrifugal force balances the gravity at the equator. So we are very slow rotating, just 10% of this critical velocity. I remember you that at the critical limit, matter from the surface of the stars is launched into planetary universe and probably will be lost by the star. You know? So you have a kind of disk, equator disk, which is expanding and which makes matter to be lost. So we are very far from this situation because we are 10% from this value. And if you take, for instance, this orbit here, so this is the evolution of the distance of the planet to the star as a function of time. Only 25 million years are represented here. The graph begins when the star was at an age of 625 million years. And the limits between the red and the white correspond to the evolution of the radius of the star when it goes up along the red giants. So if you take typically this Jupiter mass, nothing occurs for a long time. And suddenly, because the radius increases, the tides become very high. And there is a strong and rapid, let us say, drop of the distance between the planet and the star. And finally, here, the planet will be engulfed by the star. We can compute a minimum initial distance at which it will occur in this kind of configuration, which is here 2.2 astronomical unit. What could be an observation signature of this kind of process? Here you have a diagram where two quantities are plotted. On one hand, there is the surface gravity. And the surface gravity is decreasing, the surface gravity of the star. And the surface gravity is decreasing when the star is going up along the red giant because it becomes more and more large. And you know, at the main sequence, it's around 4, even 4.5. And here we are already toward the red giant branch, go toward very low value. And here you have the surface rotation, the equatorial surface rotation, kilometers per second. The dots are red giants with mass around, let us say, 1 solar masses, around 1 solar mass. What is interesting is that most of the points have very low surface metallicity and lower when you go to lower gravity, because again, by conservation of the angular momentum, since the star is expanding, the star slows down. And what is interesting is this red line here, the long dashed red line. Actually, this red line is a kind of envelope, upper envelope. I explain you why it is a kind of upper envelope here. Here we suppose that the star begins its evolution with the highest amount of angular momentum that we can realistically imagine. So we suppose that the star, at the beginning of the zero-age main sequence, starts with the critical velocity. It cannot be larger because otherwise we lose mass. So it's at the critical velocity. And then we evolved these stars assuming that the star rotates at a certain point all along its evolution. And you have this limit, you have this evolution here. And you can see that most of the points are below. But there are a few, typically E, F, with the uppercase letters, and especially A, which are much above, at least for A, it's the case. And we believe that in order to explain the high velocity of the red giant, the only way is to say that the star had some interactions, either with the companion, and if we don't see a companion, maybe because it has engulfed the planet. Now I will show you what a planet engulfment will do in this range. You have here typically the surface rotation evolving as a function of the gravity for a star beginning with 50% the critical velocity of the 0-element sequence. So here you can see that it decreases a lot, and then it goes like this. But if we have a planet engulfment, as I showed in my slide before, we have an increase of the velocity. This is the black line here, which can go up to 40 kilometers per second if the planet has 15 times the mass of Jupiter. It can go up to 30% if it has 10 times. It can go up to, let us say, 12 or 14 kilometers per second if it is a Jupiter mass planet. So we believe that these fast rotating red giants may have engulfed planets, and this is why they are rotating so fast. Is there any other way or other signature? We look at another one, maybe. We took the quantity of lithium that there is in Jupiter, and we decided, and we say, okay, let us suppose they have the same amount of lithium, and we dilute the lithium inside the planet in the convective envelope of the star, and it makes lithium-rich red giants. So we would say fast rotating lithium-rich red giants might be red giants having engulfed the planet. Yes?
At the beginning, you said the tides from the star on the planet, like transversing the momentum of the planet was the orbital was larger than
actually, it was the tides of the planet inside the stars, not the tides of the star inside the planet, which produce this. Yes, actually,
so the orbit shrinks rather than increase.
Here it will shrink because you are in a configuration, let us say, where the planet has an orbit below what we call the co-rotation radius. You see? So in that case, the planet is preceding the bump, and then it makes exactly the contrary of what I showed before. You're welcome. So I go to my second topic. Actually, it's a topic about a very famous star. It's a star among the stars, as you can say there, Betelgeuse. And as you will see, we have a very different view of some of our colleagues on these stars. And my point is not to convince you that we are right, or they are wrong, or the contrary, but maybe to explain why we have a different solution. The question is, when will Betelgeuse explode? By the way, we are not sure that it will explode. It can also completely disappear, producing a black hole that swallows the whole mass around. It's just at the limit, let us say. So it's not sure that we make an explosion. Anyway, if it will explode, we have not to be afraid. It's too far away to be harmful for planet Earth. But it will be a fantastic, I would say, sure. Betelgeuse will become bright as the full moon, and probably for a few weeks, for a few months, I don't know exactly. So as you know, it is one of these very bright stars in the sky. It's a red supergiant. And in a recent paper with Hideyuki Sayo, we had a look at the variability, the luminous variability of that star, trying to explain them by observation. And what we wanted to study is, okay, let us try to understand this observation, and let us see what they tell us about the evolutionary status of Betelgeuse. And here we have a very different conclusion than what we've been obtaining so far. Actually, we obtained an indicative diagram where we have the time. It's a bit strange because it's a logarithm of the duration before the collapse. So here we are at 100,000 years before the collapse. Here, at a few centuries. And actually, in the paper with Hideyuki Sayo, we obtained a solution that it should be relatively at the end of the, let us say, during the core carbon burning phase. So here, while other authors like Mary Joyce and collaborators have obtained that, sorry, I just forget to explain you that we have here the abundances of the main fuel at the center of the star. So hydrogen here, the helium that begins to grow because it is due to the transformation of hydrogen, then it is decreased during the core burning phase. The carbon, and here you have the carbon burning phase, the neon, the oxygen in blue, and the silicon. So it's really the whole, let us say, nuclear history of the 20 solar mass stars, something like this. So according to what I will explain, we are here. Instead, Mary Joyce thinks that we are at the beginning of the core burning phase. So it means that we are saying that the star will explode between now and 300 centuries, let us say. So it's relatively short, while the other group says we have to wait a few 100,000 years before it will explode. When we were working on that, I was saying maybe we have to submit the paper before it explodes. But okay. So the approach is very simple, you know. It's an approach to stellar evolution. You have some observed features, typically the position in the Hess-Wilson diagram. But in addition, for temperatures, you have this variability or semi-periodic variability of temperatures. And actually, this semi-variability has been decomposed in 4 periods. One with more than 2,000 days, so nearly 6 years. One around 400 days, and 2 shorter, less than 200 days. And actually, we wanted to see whether we can reproduce the observed position of the star in the Hess-Wilson diagram, luminosity, colors, or effective temperature, and these 4 periods. And actually, we can. I will maybe just discuss this part of the diagram here. You have here the period in log. So the longest period of 2,000 days is here, the shortest one of 180 days is here. You have 2 other periods. And you have the luminosity on the y-axis. And typically, if you look at the black triangle, for instance, it corresponds to, let us say, 19 solar mass stars, because it's black, which started its initial rotation with 40% of critical velocity. And each time there is a triangle here, it means that we have a pulsation or a mode of pulsation that is excited, that can be visible with a period of this value. So the observed periods are the error bars, points with error bars, and we see that in order to reproduce simultaneously the 4 periods, we have to be at the tip of the red chart. And this is why actually we need to be in a very advanced phase of the evolution during the carbon burning phase. So we can wonder. So maybe before I say that, I would like to show where we are in this diagram I showed you before. So typically I have plotted here 3 models that reproduce both the observed position, the 4 periods of pulsation, and you can see that we are during the carbon burning phase. Actually, we didn't do analysis beyond, because you know, in the massive star evolution, beyond carbon burning phase, the core is an evolution which is decoupled from the envelope. The envelope, nothing more happens. It's too short, you know. It remains a few centuries for the evolution of the star, and the Kelvin time space of the envelope is too long. So nothing happens. The envelope keeps the same structure. The core, on the other hand, evolves very rapidly because most of the energy is evacuated by neutrinos. Actually, during the carbon burning stage, we can speak about neutrinos rather than electromagnetic, because most of the energy is evacuated by the neutrinos. The neutrino luminosity can be 10,000 times the luminosity by radiation. So it's very short. We can wonder why our sorry?
10,000 times than the ELN.
Then the A20 energy, radiation, yes. Actually, you have a paper by Frank Teams, I don't know if it is him, the first authors, which have appeared recently, where they look during the whole evolution, they compare radiation output with neutrino outputs. And this is our numbers.
Only during this.
Only during the advanced phase. Actually, you have neutrino emission during the whole evolution, as you know, from the sun. We capture neutrino from the sun.
But during this explosion, 300 times.
Yes, it's right. But it's a very, actually it's very different. At the collapse of the massive stars, the process is by electron catchers, which mix, or let us say, which fusion with proton in order to make neutrons. It's a neutronization. While during this phase, it's other processes, plasma neutrino, brainstorm neutrino, Pearl neutrinos, and so on, and a little bit of, let us say, neutrino coming from nuclear reactions. But what I wanted to say now, I have lost it. Yes, I wanted to say why our colleagues do not got the same answer. Actually, it's because, you know, they discarded the longest period of pulsation as a bona fide true pulsation period. They actually consider it is what they call a long secondary period. By the way, long secondary period is just a name. It does not cover any very defined physical mechanism. It can be due to a companion that is so near from the star that it kills mass, a little bit like the evaporating planets, and produce some change in the variability, some change in the star during its orbit. So, according to them, it has nothing to do with a true period of pulsation. Instead, here, we suppose it was the true period of pulsation, radiant was it is even the fundamental mode. And if it is the case, then we cannot escape that pulsation is very far in its evolution. Of course, one way to decide between the two models, I will not say, I cannot say who is right, let's say, because I cannot be sure that it's true fundamental period of pulsation. But one way of doing would be to capture the neutrinos, because as I said, the neutrinos are emitted a lot. But unfortunately, the present day facilities, as well as some future ones, cannot capture the neutrinos which would be emitted by a star like Betelgeuse during the carbon bonding phase. One of the reasons is because the mean energy of the neutrino is too low. It's around 2 MeV. And the sensitivity is here, they will capture only neutrinos above this energy. But you can see that these facilities, typically superconducting, could maybe detect the neutrino, not due to the explosion, but the one due really to the secular evolution, one day before the explosion. What time is it now? Okay. So I arrive now to the third topic in the universe. Now we have dedicated a lot of effort in the past, let us say 20 years, to understand the physics of rotation. What rotation brings in terms of changing the evolution of life. And if there is a place, a time in the history of the universe where rotation may have played an extremely significant role, it is during the early stage. Because, as I will explain, rotation is particularly important at low magnitude. Why it is interesting to observe the first stars? Because you cannot observe it, and so we are very comfortable. When you do theory of something you cannot observe, you have much more freedom. But at the same time, you know, there are still some consequences which are observable. We are interesting to know the first stars because they participate to reionization, they drive the early chemical evolution of galaxies. We want to know if there is some signature of starbursts which are dominated by 3 mm or even 3 stars. And we are interested to see whether we can determine signature of luminous transients coming from first stars. Now you have also the frequency of black hole merging coming from this first population and so on. But I will just show you an example about what can do rotation for what concerns nuclear physics. Recently, Sophie Tsiatsu has computed new models for propulsion stars with different rotations. What I show you here is the chemical structure of a 20 solar mass star, really for a propulsion-free star. So no metal at the beginning. And what is shown is typically the structure, the chemical structure at the middle of the core-helium burning phase. So you see the helium is the gray line, which becomes a little bit smaller in the center because helium is burning. It's at the middle, so it remains typically 50% in mass fraction of helium. The blue line is oxygen, the carbon is carbon, and the red dot, the green dot here is nitrogen. So as you know, at the beginning, there was no carbon and oxygen. This carbon and oxygen is produced by helium. And there was no nitrogen. And this nitrogen is produced in the hydrogen burning shell. You see, hydrogen is this black line, it's false, and we have hydrogen burning. And it is produced because it transforms carbon and oxygen into nitrogen. But it transforms the carbon and oxygen produced by the star. So it's called what we call here primary energy, in the sense that this nitrogen is not due to the transformation of carbon and oxygen that were initially present in the star, but it is due to the transformation of carbon and oxygen produced by the star. And how this carbon and oxygen produced in the core arrives or diffused into the hydrogen burning shell is because rotation. It's because you have some turbulence. No, rotation can be maybe instability that arises, but there is also what we call the shear instabilities. When you have layers which are rotating essentially, there are turbulence happening, and this turbulence can mix these layers. There is a very famous example in the Jean-Pascal book. If you compute typically the specific kinetic energy density of a system composed of two layers rotating at different speeds, you will see that the specific kinetic energy of these two layers is above the one of a layer that will have the average rotation. So the average rotation is a lower energy level, if we can say that, than the differential rotation. So nature has tendency to decay to lower energy level. And this is the root of this shear instability. And the shear instability allows the carbon and oxygen to be transported from the helium to the hydrogen burning shell. Why now it is important, especially in atomic length? As you know, if you start with a bit, you have hydrogen burning in massive stars, like a 20 solar mass stars. But at the beginning, you have no CNO. So you burn hydrogen by the PP chain, but the PP chain do not produce enough energy in order to compensate for the loss of the energy associated. So the star has to extract energy from another reservoir, which is gravitational reservoir, which is contraction. So the star will contract up to the point where the temperature becomes high enough for activating critical reaction, which produces a little bit of carbon, which induce the CNO sign. And from the time on, you have relative equilibrium. You have that the energy produced at the center alone to compensate for the loss at the surface. This means that in a propulsion-free star, the temperature in hydrogen burning is already very near the one of helium burning. So it means that the distance between the shell and the core here is not so great because the entropy, because the change of temperature is very small. This is not the case in solar metallicity stars, or even in stars with a little bit of matter, because it will produce a much stronger contrast of temperature, a larger distance between the stars, and disfavor this mixing. So this mixing occurs only at low or in propulsion-free stars. So here you have the bump. If you start with a mass or with a rotation which is 40% the critical velocity. Sorry, I made a mistake. This is 70%, not 40%. Here you have the case, the same evolutionary stage, middle of the helium burning, but the star is rotating at 70% the critical velocity, much faster. And you can see the bump of nitrogen much higher. And you have here simply a more advanced evolutionary stage from that models. So at the end, you have a lot of nitrogen that can be expelled at the moment of the supernova explosion. By the way, not in propulsion-free stars, there are other processes which can occur thanks to this process. If you have slightly, actually what happens is that this nitrogen, which is very abundant in the envelope, can also diffuse back in the core. And it will be transformed into neon-22. And neon-22 is the main neutron source at the end of covalent burning by alpha N reaction. You know that neon 22 is destroyed at the end of the helium burning phase by capturing alpha and producing neutron. And this flux of neutron produce more heavier element than iron, which are called S process elements. And this S process element can be used to form the P process, which are proton-rich elements. And this is a point that we showed recently in this paper, where indeed all these processes can open new paths in nuclear synthesis.
So I can
Yes.
So when you have that, let's say you produce this nitrogen, then in the next generation of stars, you would start with more nitrogen than before. So actually, you could compare
Yes.
the nitrogen balances of the next
Absolutely.
and see whether
Exactly.
And
I will show you now. It's exactly right. Okay. So maybe this is this first plot is more a theoretical plot. It's not so nice, but it's interesting for me to look at it in the sense that you have the metallicity, which is increasing to the right, and here you have the nitrogen production. But it's a nitrogen production only for one mass star, 20 solar mass stars. All the stars at all metallicity start with the same initial rotation, 40% of the critical velocity. And you can see that something happens particularly around 10⁻⁵ in metallicity. And you have this kind of bump because when you lower the metallicity, actually you have one process that favors the medicine between helium and hydrogen shell, and one process that disfavors it. You know, if you look at the mixing time scale between two zones, you have to have at least two basic quantities. First is a distance, because the time scale varies with the distance to the square divided by the diffusion coefficient. The diffusion coefficient, on the other hand, depends here, mainly in these models, to the shear, differential rotation. So when you go toward low metallicity, you have that the distance decreases because the stars are much more compact. They are much more compact because of the point we explained a few minutes ago, the lack of CNO, which make the star compact, but also because the opacities are much lower. Typically, to give you an example, if you compare the radius of a 20 solar mass star at solar and proportion free, the proportion free star will be nearly more than 3 times more compact, have smaller radius than one of the solar mass stars. So it's not just 10%, more than 10%. So this, you reduce the distance, you increase the density. But at the same time, the differential rotation is mainly produced at the end of hydrogen burning, when the fuel has been exhausted in the core, and the core still contracted a bit fully the helium burning reactions. But because you start from a high level of temperature in the fuel crystal, you don't need to contract much. And this is a small shear. And this is why you go back down when you go to proportion-free stars. What is interesting, even small increase of metallicity make a huge difference here. Of course, as I said, it's for given initial rotation. If you take now proportion-free stars, but you rotate much faster, you have diamond points. So let us say that here you have a possibility to play with metallicity, but also with initial rotation. It shows, nevertheless, the point is that we need to have some clues about that in the diagram, because it has some importance for the chemical evolution. So this is the answer to your question, actually. It's a very simple model. You have here the evolution of the oxygen, which is a little bit a proxy profile, at least for the star in the halo galaxy. These are stars of the halo. It's coming from the SAGA database. And actually, what is interesting here to show is that, you know, if this is a proxy of time, up to some metallicity, only the massive stars have time to enrich just around the end. And typically, let us say up to 7.5, we can say that there is no time for AGB stars. After AGB stars, which have longer time scales, you know, massive stars is 10 million years, AGB is 100 million years, AGB can come into play and add some nitrogen. The curves correspond to a very simple chemical evolution model that was computed by visit to us last month and did this during this stay. It's a very simple model. We'll do it in more sophisticated one in the future. But if you take the yields of all the metallicity from 0 to supersolar, you include these yields into its chemical evolution model, you have the blue line here. It just accounts for massive stars. So this blue line has some sense up to V. After that, AGB stars should be included. But even up to here, you are much below the points. If you include rotation, only rotation 40%, you have the red line. And if you include only for the population-free star, a very fast rotation of 0.7, you will have the green line. So here it's a bit too early to make a very deep comparison with the observation, but what is sure is that in order to explain the high level of nitrogen observed in these metal poor halo stars, you need some mixing mechanism between the helium and the hydrogen. Is this mixing due to rotation? Maybe. Finally, I don't know how much time I have. I think 5 minutes.
5 minutes.
Okay.
More.
Okay. So what is interesting, we are recently interested in much more massive. Actually, we have created with John Reagan, we have looked at hydrodynamic simulation of the formation of stars in mini halos. And actually what it provides us are accretion rates. Accretion rate on stars when the stars are forming, and this accretion rate are varying with time because the stars are moving and they will explore different parts of the mini halo, sometimes with a higher density, sometimes with less density, and so the accretion rate varies with time. And so Devesh Nandal, who is finishing his PhD now in my group, has computed the stars that are produced from this varying accretion rate in these mini halos. And he obtained that stars between, let us say, 1,000 solar masses up to 10,000 solar masses are produced. And he computed the evolution. And this is the chemical structure of one of these stars. So here is the mass, and this is the center of the star, and it is a mass up to nearly 9,000 solar masses. And again, you have the abundances. And what is striking, this is also a population-free star. You can see that the envelope is enriched in heavy, especially nitrogen. Here it's not, there's no rotation. But because these stars are essentially supported by radiation, most of the weight is supported by radiation, they are on the verge of always being convectively unstable. And in these stars, we have many convective results, which sometimes appears in some range of the mass, sometimes in other parts, but at the end it connects them. And you have the same principle as what happened for the lower masses, where rotation was wider. Here you have convection, which is wider, which allows to produce nitrogen. So, of course, what we don't know is how much is lost, because these stars could easily, let us say, collapse at the end and form a black hole, which would be a really good. I would say that black holes are very interesting, but only producing black holes for me is a bit of pity. You should produce something else also. And let us say we imagine that indeed, because these envelopes are very unstable, we can have pulsation, as we saw for potentials, even more here. We suppose that they lose some mass. And actually, if you take these models, and we suppose that we lose, let us say, 40%, let us say, up to there, of the mass, and we look at the chemical composition of the ejecta, pure ejecta, it will produce the blue dot point around, there is a dotted line at the upper part. It is in the N over O over H diagram. So you are here. Now, of course, you will not form stars from just pure ejecta. Probably it will mix with some interstellar medium, and the interstellar medium has no nitrogen, has no oxygen, has no oxygen, it has, of course, hydrogen. So if you mix with primordial, you will go to the left. You will not change N over O because there is no nitrogen and no oxygen, but it will dilute the oxygen. So you shift to the left, and the green point corresponds to a case where you mix with 100 times more interstellar medium than there was in the H. And now, if you look at the population of massive stars predicted in the hydrodynamical model by John Wigan, you have the continuous line. So here it's not for just one star, it's for a population of extremely massive stars, let me say. And again, you have these different lines which correspond to the loss of only 10% or 40% of all the mass above the zero core. It's very schematic, I would say. But what is interesting, you know, you have this big gray domain. This big gray domain corresponds to a very conservative estimate of the N over O over H for a galaxy at high redshift GNZ11. And let us say the Marquez Chavez 2023 correspond to photoionization models, which give the red star here. What is interesting is that I don't know if it is related to these galaxies, because you know these galaxies, it has a redshift 10, it's very far away galaxy. We probably here see in the integrated light of this galaxy. So we don't know exactly whether we measure what we measure to some extent. But there are many papers which have appeared in order to explain the high nitrogen enrichment. So it's more than 3 times solar. Why it is nitrogen enriched? What we say here is that if we look at the impact on nucleosynthesis of these very massive stars, it can produce, let us say, N over O over H of near the value which are observed. But maybe it's a coincidence. Maybe it's not. Interestingly, if we use the fast rotating function-free stars model, we do the same kind of models. We obtain also the solution. What is different is the quantity of helium which is produced, and maybe useful in discrimination. But anyway, there are many other solutions to this problem. But I want to say that there are signs, not only in stars, that there are a lot of nitrogen produced in the early universe. My last topic was about the supermassive stars, which are even more massive than this one. And it is related to the fact that we observed very massive black holes in the very high redshift universe. As you know, there are black holes with 1 billion solar masses, which are observed when the universe was 1 billion years ago. So the question is how this mass has been accumulated in such a short amount of time into the black hole. In order to do that, and in order to avoid maybe unrealistic super-Hamiltonian accretion, we have to start from seed black holes, which are massive. Typically, they are 10,000 solar masses. And then people have looked at what can be the history of accretion in order to reach this high value at the current time. We are not interested in this part of history, but more what happens before. How do we produce 10,000 solar masses black holes? If you use the accretion rate, which are, let us say, the one devised by hydrodynamic assimilation for classical proficiency stars, 3 stars, we have here the case of the red line. This is actually the evolution in the Heffron-Russell diagram of an accreting object, mass, which is increasing with time, according to an accretion law given by hydrodynamic assimilation by Okubo for, let us say, normal population 3 stars. And you accrete. And the most massive stars that you can obtain by not stopping the accretion will be around 1,000 solar masses. So it means that the normal places, or let's say the places where the normal stars are formed, cannot produce seed black holes of 10,000 solar masses. Maybe 1,000 is not enough. So people have imagined that there are other places where you can form much more bigger stars. And these are atomic cooling elements. As you know, the cooling process is the key to understand the formation of stars. Because when you form stars, you extract energy from the gravitational potential. If you keep it inside the star, it will stop. It will stop at the gate. So you have to evacuate it in order to produce smaller stars. And in order to evacuate this energy, you need to have cooling mechanisms. The current universe, the cooling mechanism, more gas. But in the quantum circumstances, we have no gas, so we have either molecular hydrogen or atomic hydrogen. Atomic hydrogen is less efficient in cooling, and it is believed to be a place where it can form normal things. In that case, we have computed with Devesh Nandal the evolution of a accreting object is very different. Starting with very low free rate, and 6 solar masses per year, up to very high free rates that are predicted, I think, by the simulation, some solution by neutral Meynet when galaxies are colliding of 1,000 solar masses per year. So you have here the accretion rate that is increasing up, and here you have the maximum mass that can be produced. Maximum mass is stated here by supposing that the accretion is constant all along the formation and all along the evolution. And the star hence accreting when it ends its lifetime. And it ends its lifetime for essentially a few reasons. It can produce an iron core that collapse, so it is a normal star. It can encounter the pair instability, in which case it will explode, at least from the mass stage. And it can also encounter the general relativistic instability. And actually, up to, let us say, to this point, up to an accretion rate of 10⁻² solar masses per year, the first limit that is encountered is the end of the evolution, the nuclear end of the evolution. And for accretion rate above 10⁻² solar mass per year, the first instability that is encountered is general relativistic one. It's not seen here well on this plot, but let us say when you have you can obtain a star with 100,000 solar masses with an accretion rate of, let us say, 10⁻1 solar masses per year, and the instability will be encountered just at the end of the core hydrogen burning phase. If you increase the accretion rate, you will encounter still earlier during hydrogen burning phase, up to the point when you use 10⁻³ solar masses per year, you reach even before igniting hydrogen. So you have no star at that time. You have what we call a dark collapse galaxy. And this will produce 1 million solar masses per year. You have here the exponential diagram of such monsters, especially if you look at the most, let's say, the stars which are using the most larger rate. You can have one star that has a luminosity nearly 10 to the power 10.5. So one star can be as luminous as one galaxy. Okay, so I arrived to my conclusion. So, essentially, I search for stellar physics. Progenitor of time scale, distance scale. Very rarely, you don't need a star, or the star, the physical star is not very often involved. I just show that it's important in the standard details, giving stars for computing the orbit of the planet. I mentioned why I think that maybe petagons might explode in the next 3 centuries, and that nucleosynthesis, new nucleosynthesis tasks could be opened by rotational mixing, and rotate accretion also might be a key process for the most massive stars. Many of these processes, like rotation, can be said as a detail in the point of view of the unit. If you look at the star rotating at a physical unit, the energy in rotation is maybe 1% of the gravitational energy. But nevertheless, as I said, it can open new paths in nucleosynthesis. And as you know, there is a famous sentence by Leonardo da Vinci: the details on making perfect and better.
Thank you very much. So the questions.
Thanks. It was really great. I have many questions, but I'll ask. So the first one for the planet star interaction. So you showed you had this the star measurement that with the ABCD that substantially faster. But then won't you detect an existence of the planet which are weak? Won't you just try to search for a planet?
I see. You mean maybe we don't see the planet that has been engulfed, but the planet that remains.
Yeah, maybe you can still see.
Yes, maybe. This I don't know. I must say. Yes, absolutely. This could be a. This is, yes, and probably there would be. Yes. I don't know.
Okay, and then my second question is about this nitrogen. So when you showed the curves for the 0.4 velocity and 0.7, right? You showed that okay, you can explain some of the observation, but not. I mean, you had also observations that are above the 0.7. So then I thought, what about collisions of stars in the early universe? Wouldn't that help?
Okay. So maybe yes. No, I think that merging of stars is probably, I know this is, I will come back to see just the plot, if you allow me. You know, first of all, when we go with, maybe I agree with you that collision mentioned could be an important process for stars. Actually, there was some limited simulation by Adolf Steiner to look at what happens when two stars merge. And they deduced that first they should have strong field, and they should rotate slowly, which is a bit, I would say, non-intuitive, because you could say that when you have a merging, you know, at the beginning the stars are rotating around that center of gravity. So the angular momentum in the orbit should finish in the star. But it's not so clear. A lot of angular momentum is created also at the moment of the merge. Now, what is a bit disappointing is that it's very difficult to know what would be the consequences from the point of view of surface compositions or whether the star is mixed or not. So I don't know. Maybe. What I would say, however, for this case here is that there is another also important point to keep in mind. Is that the mixing of the ejecta takes some time to and probably the earlier we are in the universe, more localized enrichment we have. And so we expect to have large dispersion due to the fact that we cannot reproduce a given chemical composition by supposing that everything is homogenized instantaneously. And here you have to look at more localized or illuminous composition, which is not the case of the models here. Actually, the fantastic case to look at are what we call the carbon enhanced metal pore stars, CMP stars, and especially those which are qualified as no, because there is no S or R process. And these stars actually have the record of having the lowest metal density ever observed. You know, even if we look at the high redshift universe, we never observed such low metal density. The record is held at the moment by what is called the Keller star. The person who discovered it has become famous. It gives her his name. We have an average less than -7. It's only a Neptune, you know, -7. We could say, okay, it's option-free stars, but it's not, because it's highly enriched in carbon. You see, and this is probably stars which are produced by the mixture between the ejecta of one, maybe two massive stars, and some interstellar movement. And here there is a large section.
That's really what it's touched on. So one thing I was wondering was the coefficient people, because I suspect that you were the one who said yes. So I was wondering what are the fix that they have to make as well.
Yes, I wanted to speak about this topic, but finally I couldn't have time. I don't know if I can show you something about here. Yes. You know, the theory that we use for the thinking is based on the paper by Jacobson. And this paper has only one atrium hypothesis, which is absolutely inaccurate. But of course, we have to accept it. And this is not so, I would say, irrational or strange. I will explain it. If you have a star that is rotating, let us suppose that the star is a solid body. The same rotation, same temperature surface. It could be slightly different. It means that the gradient of temperature along the rotating and along the rotating will not be the same. Now the gradient of temperature is related to the gradient of change. So the gradient of temperature will not be the same, depending on the latitude. And this makes it impossible what we call the local relativity. It means that if you take a piece of the star, it will receive more heat in its field or less heat than its neighbor, because there's no relativity in it. What takes it because of that? And because of that, there will be points of that. And we have a large population which are called meridional circulation. This meridional circulation we transport on the transport in both directions, inside out or out. And we say also along the line. But what Sam said is that, you know, when you want to smooth a gradient which is like that, you have to struggle against the stabilizing effect of the gradient or the new gradient in the negative field. It is not fixed normally. And then we don't like the part, you have to so it's easy. And so it's the goal that has a strong concentrated array that makes the vacuum equal in one language. And this strong turbulence also homogenizes the chemical activity in one language. So we have a state of what we call a Scheller. In the sense that the starting is same at the point unit, which vary when you go to the now, when we say radial dependency, it's actually only for the mean value, and the equations there are changed in order to get access to the mean value of each value. And from this mean value, we can then make development using Legendre polynomial and restrict to the first term because we suppose that the local star equation is very far from any addition of this one. And also any quantity can be written as on isobar, so P is constant, theta is the collective, as a mean value, which is accessible thanks to resolving the modified self-electric equation plus a perturbative equation. So we can, to some extent, start from the 1D solution and reconstruct a 2D solution. This is exactly what we have done. It's not an artistic view, it's really computed from scalar models. And this one is still the part for that at 1.5. And you have here the equation of the angular momentum transport. And what is physically, for me, extremely interesting, you know, you have two types of terms. One term describes what the marginal currents are. And this term is what we call an advective equation. And you have a term which describes typically what we do, let us say, for the shear current, or what we do magnetic stability. And this will give the diffusion. And for the angular momentum, you need to keep this term. Actually, in many codes, and I must say that within MESA or other codes, they describe the transport of the angular momentum by the diffuse equation. This is, in my view, not so dramatic sometimes, you know, I don't want, but why it is important? Because attention can create a gradient. It can bring angular momentum from where there is movement and bring it where there is not. You know, André had the nice analogy saying it's like the circulation of money. Because you have a money goes from the important place to the you know? Advection can do the same. Not always, but can do the same. So it can accelerate some parts which are already fast rotating. The diffusion will always smooth the gradient. And I will just show you one numerical experiment that we did. It's a bit complicated, but I will just point two curves in this diagram. Here you have the radius inside the star at a given time. It's at the middle of the hydrogen burning phase. So this is the center, this is the surface. And what is shown is the profile of omega, the angular velocity. Omega is constant in the core because we suppose that in the convective zone, you have an efficient transport that makes the convective core to rotate as a solid body. And you have the black line. The black line is obtained by resolving this equation, the advective and diffusive one. Now, in our code, we did the same trick as in many other codes. We did not account for the advective term, but we include this by computing an appropriate diffusion coefficient. What will be the solution? The solution will be the green term. So you see, you have here an example which shows how big the difference is. Now, to be honest, I must say that if you use magnetic instabilities, it's less of a problem because magnetic is so strong that the angular momentum is by negative current you can manage it. So in that case, it's not so important whatever solution you may choose.
Yeah, the question is about the first part, the tides. And you say that the angular relation starts in the effect. Actually, it's speaking with the star is related to differential. So, does this confirm the question?
This is a good question. It's a good question. It's not a good answer.
I want to see which one? It's a good question. The battery is one part. Yeah. Anyway, and the comment was, so if you're right, the just is already explored, right? I just checked, it's like 600 years away. So
Yes.
already done.
So the message is on the way.
Okay, the last question.
But let's see if that's in the previous. Let's see. No, actually, the fact that now the detectors, the detectors mean that the pressure is not one day before storage. Just like that. But if it is, let's say, 10 years or 300 years or 100,000 years, it's okay. What the fact that we don't detect today is quite compatible.
So the question was, if you have a way of enhancing the flux,
You would or you
enhancing the flux, let's use the sound. Okay.
I think I don't know. About this. Of course, it would be nice to capture the materials and bring cover the phase. Actually, a long time ago, I estimated that I was once, like about 6 stars in strategy in the particle in the star. Which would be the advanced state of the evolution to eliminate the evolution. I don't remember because it's quite a very long time ago. And I don't remember sure about the physical part. But it was based on the simple element on the time scale of the length of the space, and can estimate how many massive stars are left in the last one.
Okay, so thank you very much.